Welcome back, everyone, to the Algebra Graph Theory seminar. This week we have Chen talking about bipartite walks on T-designs.
Okay, thank you, Sabrina. And today I'm going to talk about a discrete quantum walk model called bipartite walk. So the first thing we need is a bipartite graph. So given a bipartite graph, then we can have two parts based on its two color classes. Here on this example, we have two parts, C0 and C1. And given those two color classes, we can partition our edges into two ways. So if two edges have the same cell in our partition, like pi 0, if they have the same ends in C0. So similarly, if they have share the same ends in C1, then they will be in the same cell in pi 1. So in our example here, like 0, 1, 0, 5 will be in the same cell in our partition like pi 0, and say like this 0, 1, 2, 1, and 4, 1 will be in the same cell of partition pi 1. So right now we have two partitions. And given those two partitions, we can define two projections. So we let P0, P1 to be characteristic matrices of our two partitions, pi 0 and pi 1 respectively. And then we use P0 hat and P1 hat to denote the normalized P0 and P1, which means we basically just scale the column vector into a unit vectors. And then we can see P0 hat transpose will be a projection, and we call it P, and then P1 hat transpose will be another projections corresponding to the partition pi 1 as Q, we call it Q. So those two will be like, they will be constant on each cell of each corresponding partitions. And okay, so given right now we have like PQ to be projections, right now we know 2P minus I and 2Q minus I will be two reflections. So our transition matrix of our bipartite walk will be a product of those two reflections. And here is the example of the transition matrix on the bipartite graph, which just showed before, and notice that like the rows and the columns of our transition matrix will be indexed by the edges of our bipartite graphs. So in our bipartite walk, our state space will be the edge space of the graph. And some of you may realize that this two reflection model actually has been like started before, because it's originated in Zachdy's paper that Zachdy constructs a bipartite walk on a directed bipartite graph to study the quantum heating time problem. And in like, if we use Zachdy's construction, but we assign those two opposite direction arcs with the same weight, and then the resulting transition matrix will be exactly the same as the transition matrix we have for our bipartite walk. And later on, the Kono and Portugal defined a more general model called two-partition model. And that the basic framework is that you have a countable set omega, and then you define two equivalence relation, pi 1, pi 2, and just based on those two equivalent relation, you define two partitions, pi omega over pi 1 and omega over pi 2. And then you define a local operators on each cell of your partitions, and then you do the direct sum of that local operators, and then you get two operators that on your whole state space, and then you take the product of those two, and then you get the evolution operators. And actually, it's the Portugal's two-partition model is very general model because it includes so many like so many other examples, our bipartite walk will be one members of these two partition models. And other than our bipartite walk, coin walk and stagger walk will also be members of the two partition walk models. And they basically just study in their paper, they study the unitary equivalence relation between those models. But today we are not going into any other models. We're just going to focus on our bipartite walk models. And so we can see like a number of invariant of bipartite models has been started, but right now we are going to look at bipartite walk in a new perspective. What we do is like, we're going to study the Hamiltonians of our bipartite walk. So what is a Hamiltonian? So for every unitary matrix U, there will be a permission matrix H, such that you can be writing as the exponential times IH. And in such H, we call it a Hamiltonian of U. And we can see like, based on how we take the logarithms, our Hamiltonian will not be unique. So if we restrict its angle to be between minus pi and pi, and then we call the resulting Hamiltonian to be the principal Hamiltonian of U. And just following the convention here, we use the principal Hamiltonian to be the Hamiltonian of our bipartite walk. And when the Hamiltonian is skew symmetric, then it will corresponding to a skew adjacency matrix of a weighted oriented graph, which we will call H-graph, and we call its underlying unoriented and unweighted graph H-graph. So we can see when a Hamiltonian is skew symmetric, a discrete quantum walk with transition matrix U will be equivalent to a continuous quantum walk over its H-digraph at non-negative integer times. So when can we get a skew symmetric Hamiltonians? Actually, it will be largely decided by the invertibility of your transition matrix. So right now, it's a very, I will show you a very easy lemma. So we call a Hermitian matrix H is skew symmetric if and only if H equal can be written as I times S, whereas S is real and skew symmetric. So here is the Hamiltonian of the example we just showed before. So we can see the symmetric, the S here will be skew symmetric. And then I can prove that if U is the transition matrix of our bipartite walk, and let H be the Hamiltonian, then H can be written as the sum of a skew symmetric matrix H0 plus pi times E minus 1. Here, E minus 1 is the minus 1 eigenmatrix of U. So just use the lemma we just showed before. So because E minus 1 will be real, so if we want the Hamiltonian to be skew symmetric, we want the minus 1 eigenspace of U to have dimension 0. So we can eliminate this real matrix. And then I can show that if the Hamiltonians of our bipartite walk is skew symmetric if and only if the adjacency matrix of the bipartite walk of the bipartite graph is invertible. So when the case U has an eigenvalue of -1, so here instead of considering the Hamiltonians of U, we consider Hamiltonian of U squared. In that case, we just get rid of the eigenvalue -1, and then we study the corresponding H-digraph and the H-graph corresponding to the Hamiltonians that the Hamiltonian of U squared. So the spectral property of the transition matrix U will be the main machinery we use to analyze the Hamiltonians of U, and a complete characterization of the eigenvalues and the eigenvalue space and eigenspace of U can be found in Harmony's PhD thesis. And some of you may know that Harmony's PhD thesis is about another discrete quantum walk model called vertex phase walk. But vertex phase walk will actually can be considered as a special case of our bipartite walk. So we can still sum up like harmonious results. And if our bipartite walk is regular, then actually the spectrum of the transition matrix will be determined by the spectrum of the line graph of our bipartite walk, of our bipartite graph. So actually, it will be an advantage of using bipartite walk. That is, in incidence matrix of a bipartite graph will have a very nice form, because the incidence matrix of the bipartite graph will have its row indexed by the vertices of your bipartite graph, and the column will be indexed by the edges of your bipartite graph. And then if vertex I is the end of an edge j, then the ij entry of incidence matrix will equal 1. So we can see the incidence matrix of bipartite graph can be written in terms of P0 and P1, and this P0 and P1 are the characteristic matrices we define when we define our bipartite graph, just based on bipartite walks, just based on the partition we defined on our bipartite graphs. And we let LG to be the line graph of bipartite graph. And when the graph is regular with degree D, and then B transpose B can be written in terms of identity and then the adjacency matrix of line graph. And also, just because of this form, we can also write it as the sum of two projections, P and Q. And then we just take the square of these equations and then use the fact that P and Q are projections. We can write them as, we can see like PQ plus QP can be written in terms of adjacency matrix of line graph and identity matrix. And then we can write U plus U transpose in terms of adjacency matrix of line graph and identity matrix. And then if we assume the spectral decomposition of the adjacency matrix of line graph to be of this form, and then we can write as U plus U transpose just in terms of the eigenvalue of adjacency matrix line graph and its eigenmatrix. So actually we can have another way to write U plus U transpose, that is using the spectral decomposition of U. And just compare those two equations, because their spectral decomposition will be unique. Then by comparing those two, we can get the following result. That is, the real part of the eigenvalue of the transition matrix U is determined by the eigenvalue of the line graph and the degree of your bipartite graph. So since the eigenvalue of your transition matrix always comes in complex conjugate pairs, once we know its real part, we will know its complex part. So we say when the bipartite graph is regular, the spectrum of the line graph will determine the spectrum of the walk. And also we can see the real part of the eigenmatrix of U will be determined by the eigenmatrix of your line graph. Okay, right now we're going to see easy examples of our bipartite walk. That is the bipartite walk over paths on 8 vertices. And we can see the transition matrix actually will be a permutation matrix of order 7. And this is true for any paths and even cycles. And for the bipartite walk on paths, we know the transition matrix will be a permutation matrix of this form. And when the n is even, the transition matrix of the bipartite walk on Cn will also be a permutation matrix of this form. And we also know the H-digraph of the bipartite walks on Pn and Cn. So know that when n is even, the adjacency matrix of Pn will be invertible. So the H-digraph will be will corresponding to the Hamiltonian of U, and it will be oriented. It will be oriented Kn minus 1. And when n is odd, the adjacency matrix of Pm will not be invertible. So which means in that case, the Hamiltonian will be the Hamiltonian of U squared. And since when n is congruent to like 1 mod 4, even U squared will still have minus 1 as eigenvalue. So we omit the case n congruent to 1 mod 4. We only consider the case n congruent to 3 mod 4. And then in that case, the Hamiltonian will be Hamiltonian of U squared, and then the corresponding digraph will be 2 copies of oriented K n minus 1 over 2. And we can get a similar result for Cn. So it just depends is the H-digraph will either be 2 copies of oriented Kn over 2 or 3 copies of oriented Kn over 4. Just depends on n is divisible by 4 or not. So just use this result. We're going to construct some interesting continuous quantum walk. One of the work we're going to construct with like interesting phenomenon is the continuous quantum walk that has universal perfect state transfer. So what is perfect state transfer? So we say let U to be a transition matrix of a continuous quantum walk over graph G. Then we say if it has perfect state transfer from A to B at time t, if the ABN, the norm square of the AB entry of your transition matrix will equal 1. And then we say a graph has universal perfect state transfer if it has perfect state transfer between every pair of its vertices. So here we see, because the bipartite walk on P8, it will have its transition matrix to be a permutation matrix of order 7. So we can see the continuous walk over its digraph, H-digraph, will have universal perfect state transfer. So here is the H-digraph of bipartite walk over P8. So it will be K7, and then we just assign weight to the arc according to the Hamiltonians. We can see the resulting graph, the continuous walk over the resulting digraph will have universal perfect state transfer. And actually, I can develop a formula for like how we assign arcs on the complete graph. So just based on the example we showed before, I can show that if we assign edge of Kn minus 1 with the weight list, and the resulting graph will have universal continuous walk over the resulting graph will have universal perfect state transfer, and the perfect state transfer that between any 2 states will happen within time at most n minus 1. And another class that will have very nice form Hamiltonian is the incidence graph of the design. So a quick recap. So what is a T design? T design is an instance structure with its point set P and L if the structure, if it has parameter less, and then we know the point set will have size B, the line set will have size B, and every point will lie in exactly R lines, and every lines will contain K points. And because it's a T design, so each T point subset of your point set will be contained in exactly lambda T lines. And then its incidence graph will be a bipartite graph with its point set and line set to be 2 of its parts. And then if 2 vertices are adjacent in its incidence graph, if and only if they are incident in the design. So when the design is symmetric, that is K equal R, the Hamiltonian will be of a very nice form, which means it will the corresponding digraph will have constant weight. So to be more specific, then we will have the Hamiltonian in this form. And because when the design is symmetric, its incidence graph will be invertible. And then this will be the Hamiltonian of U. When the design is not symmetric, that is the adjacency matrix of its incidence graph is not invertible, then the H will be the Hamiltonians of U square, then we just change this 2i to 4i. So we can see it will not cause that much difference. So from now on, we just assume the design symmetric, the adjacency matrix of incidence graph will be invertible. And in that case, we will have the skew adjacency matrix in this form. And here we can see like the weight, the constant weight is this. Okay, so one of the machinery we're going to use to study our Hamiltonians over the design, that is the three-class association scheme on flags. That is the scheme we're going to use here is a modified version of the association scheme that's constructed by Chakravarti. And first, what is a flag? So if we given a tuple that the first component is indexed by its point and the second components are the lines. So if the point is incidence to the lines, then the point line tuple will be a flag. So there's the three-class association scheme is that if given two flags, we say two flags are one associated, they are either share a point or they share a line. And we say a flag A is 2A associated with flag. So here is the example. If this flag A is 2A associated with this flag B, if the point and lines are different, but the point of A will be contained in the line of B. And similarly, we say a flag A is to be associated with flag B if AB will have different lines and different points, but the point of B will be contained in the line of A. So we can see if a flag A is to A associated with B, then B will be to B associated with A. And we say two flags are two associated if they are either 2A or 2B associated. And also we note that two flags can be both 2A and 2B associated. And we say if two flags are not, they are neither one associated and nor two associated, we say they are three associated. And just use the association scheme we just defined before, we can get some information of our H-digraph. That if G is the incidence matrix of a T design, and then we consider the bipartite walk over this incidence graph, then we know its H-digraph will be Eulerian with in degree and out degree to be equal k minus 1 times I times R minus lambda 2, and then the H-digraph is weakly connected if and only if it is strongly connected. And its incidence graph, if the incidence graph has greater or equal than 6, then the H-digraph will have diameter 2, and then if it has girth 2D with D greater or equal than 3, then the H-graph will have girth D. And here is just a quick example of projective plane of order 2. So these both lines here are the neighbors of E0 in the H-digraph. And here is the H-digraph of projective plane of order 2. And we can see because the projective plane of order n, its parameter is determined by the orders. So the in degree, out degree can be written just in terms of the order of the plane. So yeah, it will have very nice form. And actually, because of the instance structure, give us a very convenient way to understand the relation between those flags. We will see the H-digraph actually can be written in terms of the distance graph of the line graph of the instance line graph or incidence graph. So actually, the H-digraph can be written in terms of the i's distance matrix of the line graph of the incidence graph. And when the design is the partial linear space, which means the incidence graph has greater or equal than 6, then the H-graph will be distance 2 graph of its line graph. But notice here, like I and the I's distance matrix of the line graph, although it will form a 0-1 basis of a coherent algebra, but it's not necessarily commutative all the time. But later we will show an example that it will actually like be commutative, so it will form an association scheme. So yeah, like before when we talk about the T design, we require T to be greater or equal than 2. So here is the class of incidence structure that is like one design, that is generalized quadrangle. We say a generalized quadrangle, we use GQST to denote them. They are one design, and we can see the parameter can be written in terms of T, S and T. And just for our purpose here, we define a non-degenerated and generalized quadrangle to be an incidence structure whose incidence graph has diameter 4 and girth 8, and will have a minimum degree at least 3. And if we let PQ to be the orthogonal projection that comes from the bipartite walk over the incidence graph of our GQST, then the algebra generated by those two projections will form a homogeneous coherent algebra. And we know every coherent algebra will have a unique basis that consists of 0-1 matrix. And right now we are going to define the unique basis of 0-1 matrices, consists of 0-1 matrices. And I will just define those Mi to be a 0-1 matrix, and each of those I will corresponding to a relation between two flags. So I define M1 to be the identity matrix, and M2, the ij entry of M2 will equal 1 if I and j, flag ij will share same line, and similarly M3 is equal 1 if ij share the same point. And M4 and M5 will corresponding to the relationship between two flags to be 2A or 2B associated. So yeah, notice that M4 transpose will be M5. Yeah, okay, so we still have like 3 other matrices to define. This M6 is a little bit complicated. We say the ij entry of M6 equal 1 if, okay, see the drawing here. If we say the flag, if we say the flag I is 2A associated with a flag K, and then our flag J will share the same line with the K, and then ij entry of M6 will equal 1. Similarly, for M7, we say if I is 2B associated with flag K, and then flag J will share the same point of this flag K, then ij entry of M7 will equal 1. And for all the relations that is not defined between two flags, that is not defined through like M1 to M7, we use MA to characterize it. So MA will be the R1 matrix J minus the sum over like M1 up to M7. So we can see the sum of all those MIs will be the R1 matrix, and MI, the sure product of MI MJ will be 0 if I not equal J, and will be MI if I equal J. So we can see they are actually like formal bases. And yes, so we can see the algebra generated by PQ will be homogeneous, unless the set M1 up to M8 will be a unique basis of this algebra that is that consists of 0-1 matrices. And one nice thing about the regular generalized quadrangle GQSS is that we can have a association scheme that comes from the algebra generated by PQ, because the line graph of the incident graph of GQSS will be distance regular of the with diameter 4. So if LAIG is the ice distance matrix of the line graph of the incidence graph of GQSS, then this set will form association scheme, and then we can see like each of these ice distance matrix actually can be written as this the sum of the basis of the matrix of the algebra, which is defined before. And then in this case, the bipartite walk on the GQSS, there will be an association scheme A that lies in the algebra generated by P and Q. And use that, we can analyze some like behavior of our bipartite walk. First is that all the flag states, the flag will corresponding to an edge of your bipartite graph. So all the flag states will be the cospectral in bipartite walk that define on the incidence incidence graph of the GQSS. So because why is that? Because the skew adjacency matrix of the H-digraph will lie in a homogeneous coherent algebra, which means when we take the power of the skew adjacency matrix, it will always have constant diagonal. Then it means the H-graph will walk regular, which will implies that all the vertices of H-digraph is cospectral. But unfortunately, like no two states will be strongly cospectral in bipartite walk that define on the incidence graph of GQSS. Because we know like the spectral decomposition of the transition matrix is this, and then because the transition matrix lie in the algebra, and we can write in, because there's spectral idempotent is a polynomial, can be written in terms of the polynomial of this U. So we can see like this spectral idempotence is also lying in this algebra. So we can write it in terms of the 0-1 matrices basis, which is defined before. And we say two flags are strongly cospectral if and only if the ith column of the eigenmatrix of U will equal to plus or minus the jth column of the exact same of the eigenmatrix of U, and just use this equation. That means the ith column of MK will be the same as the jth column of MK for all the case. But we know each K will corresponding to a relation between two flags. So this equation breaks pretty quick. Like for say M2, then M2 means if M2 is characteristic matrix for two flags that share the same lines. So we know there's no two different flag. If I is not equal J, then there's no two different flag that will share the same set of the cellmates in the line cell. So this cannot be true. So we know there's no strongly cospectral pairs in the bipartite graph, in the bipartite walk defined over GQSS. So the question follows that is like, so far in all example we find if there's a homogeneous coherent algebra coming from the bipartite walk over T design, then the design will be flag transitive. So I just wonder if there's any like non-flag transitive design that will also allow a coherent algebra. And we can also see because the coherent algebra actually provides a new tool for us to analyze the behavior of the bipartite walks. So I just wonder, is there any other way we can just make use of this new tool? Yeah, and another like interesting matrix that coming from the bipartite walk is the average mixing matrix. So first, what is a mixing matrix? So mixing matrix of a transition matrix U at step K is the shear product of U to the K and the complex conjugate of U of u to the k. And here I can develop a formula for average mixing matrix. It can be written as the sum of the ER short product of the composite conjugate of the ER. So some of you may find it's actually like the formula for the average mixing matrix of bipartite walk will be very similar to the average mixing matrix of a continuous walk. So continuous walk here is instead of using like ER short product, ER composite conjugate, it's ER like ER short square. So it will be very similar. So here's all the properties of the average mixing matrix of bipartite walk. So many of you may already know this, that those properties also holds for average mixing matrix of a continuous walk. But actually there's one difference, like at least one difference. We know like if a graph is undirected and connected, then all the entries of average mixing matrix of a continuous walk will be positive. But that is not true for average mixing matrix of bipartite walk. So I think that is because of the H-digraph is oriented, but I cannot exactly figure out like under what kind of circumstances we will have zero entries in our average mixing matrix of bipartite walk. And if there is zero entries in like say IJ entry, then what is the relation between those two states? And one like interesting one interesting quantum walk that coming from the average, we can see from using the average mixing matrix is sedentary quantum walk. What is a sedentary quantum walk? That is, if we have the transition matrix of the walks over family of graph, then we take the limit as n approach infinity, then the average mixing matrix will be like converged identity matrix. And then one of like very surprising example is the average mixing matrix. Is that average mixing matrix of the continuous walk over the complete graph Kn will actually give us a sedentary quantum walks. That means like the continuous quantum walks over complete graph Kn will actually like they tend to just stay where they are as time involved. They don't want to move. They just stay at home. Yeah. So two more sedentary family we can find using bipartite walk. That is the regular generalized quadrangle GQSS and the projective plan of order n. And another way to use our average mixing matrix is to find equitable partitions. So the lemma here says like if we have automorphism of if we have automorphism sigma, then if the sigma map A to B, and then we let P to be the permutation matrix that associated with this automorphism, then we know P times the eighth column of the average mixing matrix will give us the bth column of the average mixing matrix. And right now, okay, we are going to introduce a way to let us have the partitions based on our average mixing matrix. That is, if we just pick like the ith rows of the average mixing matrix, and then we say if just look at the rows, we say if two entries have the same value, then they will be in the same cell. And then this will give us, so each row of the average mixing matrix will give us a partitions. And just use the lemma I just showed, I can prove that if the partition we get here, just using the method I just described, if the partition we get will be equitable, then it will be orbit partition that is raising from the subgroup of the automorphism group of the line graph, such that every element in that subgroup will fix the I element. So actually, equitable partition will be very handy when it comes to analyze like if a graph have perfect state transfer or not, because we know if say there's a perfect state transfer from A to B in graph G, then if there's an equitable partition that A is a singleton, then we know B also should be a singleton in that equitable partition. So we can very quickly to decide if like a vertex, if a state A have perfect state transfer in a graph or not. So we can see like equitable partition will be very like useful when we try to analyze the perfect state transfer in our walk. So we wonder like when there will be an equitable partition like coming from average mixing matrix. That is because like using the method I described before, it's not always will guarantee you an equitable partition. Okay, so right now I'm going to ask more like ambitious questions. That is like, because in all examples of bipartite graph we observe with perfect state transfer, the graph will always have minimum degree at most 2. So I would like to know if there's any graph with minimum degree greater than 2. That the bipartite walk defined over that will have perfect state transfer. And finally, I will show you a very interesting examples. This H-digraph actually is coming from the bipartite graph of the bipartite walk. Over the bipartite graph, I just show at the beginning of the talk, and this is the transition matrix of the bipartite graph, of the bipartite walk. So we can see here, just look at the first columns of the transition matrix here. We know like at time k equal 1, there will be a perfect state transfer from E1 to E6. But when I do the calculation in Sage, I check up to steps, right now, it's like 300,000 steps. There's no perfect state transfer from E6 to E1. So there's no return to like E1, but it will come very close to 1, but it will never actually get to 1. Yeah, that's all I have today. Thank you.
Thank you very much. Are there any questions for Tina? Well, I have a question.
Okay.
How did you come up with this example?
This one?
Mm-hmm.
I mean, because we know if the minimum, if the bipartite graph, you have one of its vertex will have degree, say 0. No, it has this degree like 1 or 2. Then we will guarantee entry 1 in your transition matrix. So it will be a trivial like perfect state transfer because it will happen at time like k equal 1. So, but also if we break so we say we increase the degree of the vertex. Once it's go over like 2 or 3, will not have those. It will not have like entry 1 in your transition matrix. So you probably will not have, at least we know it will not have like trivial perfect state transfer, right? So I just wonder if those those fractions here, can we get, when we take the power, will it like ever sum up to 1 at some point, and then I just check, and then it doesn't. But I mean, it could be happening like later.